Swayam Prabha. Digital India. Educated India.
Students, welcome again to one more lecture on the topic of consolidation and settlement. This is going to be the 6th in the series. I think, as always, I can start with briefly reviewing whatever we had seen in the past one or two lectures, and then pass on to new material in this lecture. So, in keeping with that, let me pass on to one slide, the starting slide. This shows that in the last lecture, primarily we dealt with the derivation of the mathematical expression for one dimensional consolidation. Unless we express the mathematical way the phenomenon of consolidation, there is no way we can possibly predict the amount of consolidation that will ever take place if and when a building or any other structure is erected. That is, we must know in advance, we must have a method to calculate in advance what is the likely settlement that a structure is going to undergo, and it is in that context that the derivation of the mathematical expression is important. We had already seen in one of the earlier lectures that we had to make several restrictive assumptions, but practice has shown that these restrictive assumptions are not really inducing any serious errors. For example, we had idealized the medium, we had idealized the process of consolidation. The process of consolidation was considered to be a one dimensional process. Now, based on all this, we derived an expression for mathematically representing this phenomenon. What is this phenomenon basically? This phenomenon is basically one of water flowing out of a soil element under the action of a load, and correspondingly the soil element undergoing a certain amount of compression, essentially due to the compression of the voids, that is essentially due to reduction in volume of voids. So, the clue to the derivation of the mathematical expression lies in equating these two, that is, what is the rate at which flow of water takes place from the element and what is the rate at which the pore volume reduces. If you equate the two, actually they have to be equal, they must correspond to each other. That gives us a method to see how the flow is taking place and how the dynamics of the hydrodynamic phenomenon is, and then we are able to also see how the compression phenomenon takes place. And since the phenomenon of flow is related to time, we in turn are able to relate the process of compression also to time, and that is essential, because only then we will be able to predict at any given stage what will be the consolidation and what will be the settlement in a structure. Okay? Because this is important, because we had already seen that to compute the total amount of settlement or total amount of consolidation that is likely to take place, we do not really need a detailed mathematical derivation. This derivation is necessary in order to find out the so called time rate of settlement. Okay, let us proceed further. So, this slide briefly summarizes the beginning of the derivation for the mathematical expression. Rate of outflow from the element is equal to the rate of change of void volume, and the volume is delta x, delta y, delta z, and this led us to the derivation of the differential equation for consolidation, which is Cv del 2 u by del z square equal to del u by del t. This expression shows that u is a function of z as well as a function of time. The constant Cv that has come in this expression is known as the coefficient of consolidation, and we have to now solve this differential equation and find out what is the relationship between u, the excess hydrostatic pressure, and the two parameters z and t on which it depends. Let us see the next slide. See, this slide shows the sequence in solving this basic phenomenon. This being a differential equation, as is the normal practice, let us assume the type of solution, the possible pattern of the solution, and then try to check that if this has got to be a solution for the given differential equation, what is the way to solve this. So, we are assuming that the excess hydrostatic pressure is a function of, if you see the slide, u is a function of Fz and phi t, where Fz is a function of only depth and phi t is a function of only time. Since these two are independent functions involving independent variables, this is a process known as separation of variables. We can now express these or substitute these in the differential equation for C involving Cv delta 2 u by delta z square equal to del u by del t, and then we get this constant. Once we have this constant, we can in fact formulate two equations, one for z and one for t, which if solved will give us the total solution for the differential equation. So, the total equation or the total solution for the differential equation is a product of the solution for Fz and the solution for phi t. So, Fz into phi t, if we multiply, we get u. Now, Fz involves a sine and cosine function, and there are constants there C1, C2, A, and phi t also involves a constant C3 in addition. Now, when you multiply these two, some of these constants also get multiplied, and therefore, we can combine these constants and we get a simpler equation like this: u equals C4 cos Az plus C5 sin Az e to the power of minus a square Cv t. Okay. So, now this is the solution in which the constants are unknown. If we determine these constants, basically there are three constants C4, C5 and A. If we can determine these constants, automatically now the solution is ready. To determine these constants, always we need conditions. We need to know some aspects of the phenomenon which we are trying to study. For example, this phenomenon includes or involves z, which means the boundaries of the problem, the geometry of the problem. Now, if we know the value of u at some values of z, that can be used for calculating some constants. Similarly, if we know the value of u at some known value of time, that can be used for calculating some constant. So, that is precisely what we will be doing. We did in fact, we defined the so called boundary conditions and the initial condition. Let us take a look at the boundary conditions and the initial condition. The boundary conditions were at the top of the clay layer and at the bottom of the clay layer, the value of pore pressure, excess hydrostatic pressure, that is 0 for all times, and the initial condition is at t equal to 0, the pore pressure is uniform throughout the depth from 0 to 2h, it is equal to the initial pore pressure ui. Based on all this, we derived essentially expressions for three parameters. The three parameters for which we derived expressions are: 1, the excess hydrostatic pressure, but just knowing the pressure alone is not our objective. Our ultimate objective is to know what is the amount of consolidation that has taken place at any given point of time. So, we need to know the so called degree of consolidation. Why we resort to defining the consolidation in terms of a degree is, we know the total consolidation. We can always compute the total consolidation without resorting to this mathematical expression, by simply knowing the change in void ratio over a change in stress range. Now, once we know the total compression that is likely to take place, the compression at any point of time can be expressed as a percentage of that, which is what we call as degree of consolidation. There are two ways we will express the degree of consolidation. One is uz, that is the degree of consolidation at any depth z, which is nothing but the amount of consolidation that has taken place at a particular time divided by the total consolidation that is expected there. And another parameter that we use is u, which is basically the average of all u values over the depth z. So, we have expression for u, small u, we have expression for capital uz, we have expression for capital U. These are the three basic expressions that we derived last time, which we will be using in our computations. The expressions are, let us take a look at these slides. U is equal to this. You can see that it is a function of a parameter capital T, which is nothing but Cv small t divided by h square, and it is known as the non-dimensional time factor. T is usually written as Tv, V standing for vertical direction. That is because a little later we will also be seeing another form of consolidation, which is not only vertical, but it is also radial in direction. So, to distinguish T for vertical from the other forms of consolidation, we have used the letter Tv, and uz, on the assumption of equal excess hydrostatic pressure with over the entire depth at T equal to 0, from that, and if that value is equal to u0, we get the degree of consolidation at any depth z in terms of again the parameter capital T, the parameter h. The parameter h that has come here is known as the longest drainage path, because if you recollect, all these equations have been derived on the basis of the time taken for flow to occur, that is the rate of flow of water from out of the element. Okay. So, h is therefore the distance of travel of the water, that is the maximum so called drainage path. Then the average consolidation has this expression, which again is a function of capital T. Now, let us see some details of the actual values of these degrees of consolidation. That is what we will be doing in today's lecture. In today's lecture, we shall try to understand the importance of this consolidation equation, and you have seen that in this consolidation equation now there is still one parameter Cv, which is not dependent upon the initial and boundary conditions. This is not a constant which depends on the initial and boundary conditions, but it is a material property. So, this Cv needs to be determined by some experimental technique, and we already know that for consolidation phenomenon, for studying the phenomenon of consolidation, we have an excellent technique, the experiment called the odometer test. So, we shall also see how to use this odometer test to compute the coefficient of consolidation Cv, and then we will follow it up with one or two examples on the use of these values in computation of settlement, okay, particularly the time rate of settlement, that is how much settlement will take place in any given at a given time. So, to begin with, let us take a look at what are known as isochrones. See, we have just now said that as the depth varies, excess hydrostatic pressure also varies, and at any given depth it varies with time as well, and that is very conveniently represented in terms of curves of equal time, isochrones, and we have such a curve which can be in fact derived from the expression for uz which we saw in one of the previous slides. Once we know the expression for uz, in that expression we can put different values of time, and you know that time is expressed in fact in terms of the non-dimensional time factor CVT by h square. So, we shall express time in terms of this non-dimensional parameter TV and substitute that in the expression for uz, then we will know how the variation of the excess hydrostatic pressure is with respect to time and depth. And the isochrones in fact depict this. Along the vertical axis we have the depth, again in non-dimensional form, depth divided by the total thickness, and along the horizontal axis we have the consolidation ratio uz, that is the degree of consolidation at any depth z. And you know that it has to be 0 at the top, 0 at the bottom, and it has to vary according to a law which is given by the expression for u. And keeping time constant, time means the time factor t constant, and making it range from 0 to 0.9 in steps of 0.05, we can generate a series of curves as shown here. These are all the curves, each one corresponding to a different time, but constant value at all points on a given curve. Those are therefore known as isochrones. You will find that we have t equal to 0 and going up to t equal to 0.9, and 90% consolidation at any given depth and any given time would correspond to a time value of 0.848, whereas 50% consolidation will correspond to a value of 0.197. Now, these two values also have been arrived at by substituting the degree of consolidation in the expression for degree of consolidation and computing the corresponding t. So, either you can substitute capital T and go on finding out how the degree of consolidation varies, or for a given degree of consolidation, say 90%, you can find out the corresponding time, and that is shown here. For 90% we have 0.848 and for 50% 0.197. Here is again the average degree of consolidation over the entire depth, and once again you find that at time factor 0.197 the average degree of consolidation over the entire depth is 50%, whereas 90% consolidation takes place at 0.848 time factor. Now, you will see that we find that the point of 100% consolidation is rather difficult to locate. It takes theoretically infinite time, but in practice it takes several dozen hours. So, if you apply an increment of load and wait for a very sufficiently long time, then there are chances of the dial gauge reading in the odometer test becoming virtually constant, indicating that the level of 100% consolidation has been reached. Okay. Now, we very often need this UT relationship in two ways. For a given degree of consolidation or average consolidation, we would like to know what is the time that is going to be taken by a given structure, or for a given structure at a given time what is going to be the amount of consolidation that would or would have taken place. Okay. So, we need these values. We have already seen in the form of graphs, two graphs or two charts, how u versus t, but it is more convenient to use a lookup table like the one which is shown in this slide. In this slide you find a lookup table u TV, u varying from 0.1 to 0.9 and TV varying from 0.008 to 0.848, and for known reasons u equal to 1 has been left out here, and two values which have been highlighted are those corresponding to 50% consolidation and corresponding to 90% consolidation. These two values in particular are very useful, as you will be seeing shortly. There are two other expressions which are conveniently used they are slightly simplified forms of the expression for u versus t, and they are shown here. You find u is approximately equal to root of 4 TV by pi as long as TV is less than or equal to 60% or 0.6 rather, and u is equal to this as long as TV is greater than 0.6. Actually, I would like to make a correction at this point. This should have been 0.2. As long as TV is less than or equal to 0.2, you will find that u is proportional to this or equal to this, and as long as TV is greater than 0.2, u is equal to this. The most important issue now is the determination of the parameter coefficient of consolidation. Coefficient of consolidation can be very conveniently determined from the odometer test. There are two methods for this purpose. One is devised by D.W. Taylor, a well known soil mechanics engineer, and another by A. Casagrande. What is special about these two methods is they are both curve fitting methods. That is, we get an experimental curve of compression versus time, and we do some curve fitting on these in order to get certain data on the basis of which we can compute the value of CV. CV is basically dependent upon t, small t, and therefore, if we can get two values of t and the corresponding degree of compression in an experiment, we will be in a position to compute the value of CV, and that is what we try to do. There are two different approaches. One is that of Taylor, which is known as the square root of time fitting method, and another Casagrande's, which is known as the logarithm of time fitting method. Let us take a look at the square root of time fitting method. As I mentioned, both these methods are dependent on the fact that there is a similarity between the theoretical consolidation relationship and the experimental compression relationship in a consolidometer test. The meaning is, in a theoretical consolidation equation, we know the precise relationship between u and t. We have seen it in great detail in several of the slides just now. U versus t. Now, if you look at it a little bit carefully, this capital U is nothing but the representation of the compression of the voids in some terms, and capital T is nothing but a representation of the time elapsed. So, the relationship between capital U and T has to have some similarity to the plot of compression, that is dial gauge reading variation with respect to time. It is based on this similarity that the methods of curve fitting have been evolved for determining CV. What Taylor has done is, he has used dial gauge reading versus root of time and considered to be similar to U versus root of capital T, whereas Casagrande has taken dial gauge reading versus logarithm of time as similar to degree of consolidation versus logarithm of capital T. Let us take the square root of time fitting method and see how that operates. Being a curve fitting method, essentially it is a graphical procedure. So, the theoretical U versus root of TV, if you take, degree of consolidation is plotted here in the vertical direction and root of time is plotted in the horizontal direction. we had seen earlier that this u versus t curve was a curve going somewhat like this, whereas now we find that once it is plotted against root of time, it has become almost a straight line. Now, this straight line is the basis for comparing this curve now with a curve obtained from typical odometer test, a curve of dial gauge reading versus root of time in the method. So, the initial part of the theoretical u versus root of TV curve is found to be linear. It is linear up to about 60% consolidation. The point corresponding to root of T90 is found to have an abscissa of 1.15 times that corresponding to the extension of the initial linear part. Let us take a look at the curve again. See, the point corresponding to 90% consolidation here is found to have an abscissa which is 1.15 times that of a corresponding point on the line extended here, and that is a basis for determining CV. That is, we take an identically similar looking curve, that is the curve of dial gauge reading versus root of small t, and in this we try to locate in fact that point which has got an ordinate which is 1.15 times that on this straight line. So, suppose this red line represents the curve of dial gauge reading versus root of time. What we do is we find out the starting point of this curve, actual starting point of this curve, because original dial gauge reading may be D0, but there is a certain amount of seating requirement, that is when you apply the load, initially the pore gases get compressed and expelled, and therefore, the actual time at which the hydrodynamic phenomenon starts can be taken as corresponding to the dial gauge reading ds. So, ds for all practical purposes is the initial dial gauge reading, and that is the straight line part of the u versus root t curve. So, the straight line starting from ds and tangential to the red line is considered to be similar or analogous to the straight line part of the capital U versus root of capital T curve, which we saw in the previous slide. So, all that we now need to do is to draw another line, that is this yellow line, which will have abscissa which will be 1.15 times the abscissa of this line starting from ds, this tangent starting from ds, and that is precisely what is shown here. If this tangent straight line can be considered as the line which may be denoted as x line, then this yellow line is nothing but x1 line, which is having abscissa which are 1.15 times those of the x line, and where this line cuts the red curve, that actually this should have been cutting here, that is the point corresponding to 90% consolidation. That is in fact, that is, you can see that it is cutting somewhere here, this yellow line is cutting the red line somewhere here, and that is the 90% consolidation point. And once we know D90, we will know T90 or root of T90 for that matter. Once we know root of T90, we already know there is a relationship between small t and CV. We know the sample thickness in the odometer test. We know that we are providing double drainage on both sides in the odometer test. So, we know what is the maximum drainage path, it will be nothing but half the thickness of the sample. That is the maximum distance that water from the center of the sample has to travel in order to be out of the soil element. So, root of TV corresponding to 90% can be determined from this graph. Once we know that, since we already know capital H and we also know that the capital T value is 0.848 for 90% consolidation, we can use all this information for calculating CV. So, if you have the initial dial gauge reading D0, first you have to work out the corrected 0 dial reading after accounting for gas expansion and so on, because that is the point where the straight line part of the curve will cut the y axis. So, D0 minus ds is the initial compression of the pores due to compression of gas. Now, once we obtain ds and root of T90 graphically as shown earlier, we can easily determine Cv. The graphical procedure, as I mentioned earlier, is going to consist of two parts. One is drawing the straight line portion so that it meets the vertical axis at ds, and then extending it, and then taking a second straight line with abscissa equal to 1.15 times those of the first straight line, and finding out where it intersects the red curve, and that is the point corresponding to root of T90. Finally, once we know capital T90 is equal to 0.848, we have a method to calculate Cv, since we know small t90 and capital H, which is nothing but half of the average thickness of the soil sample in the odometer test. Now, the explanation for the logarithm of time fitting method becomes much simpler. Here, degree of consolidation is plotted against log of Tv, that is against Tv to a log scale, and this is found to be very close to a parabola, and it is found that this is similar to the experimental curve, where we plot dial gauge reading with time. So, we will now be seeing the logarithmic method of Casagrande, in which u versus log t is used, and it is seen that the u versus log t curve is similar to the dial gauge reading versus log time. The basis, as you can see in this slide, is that u versus log TV curve is similar to the curve for dial gauge reading versus log of time. In this method, instead of T90, we locate T50. So, we need to locate the starting point corresponding to ds, and we need to locate the point D100. So, once we know the dial gauge reading corresponding to 0 and to 100, we can interpolate and find out the dial gauge reading corresponding to 50 and the corresponding time factor capital T50, and that is the method. So, here is the explanation for the method in pictorial form. If this yellow line represents the dial gauge reading versus logarithm of time, then first step is to take this as a parabola, because it is found that in the theoretical u versus log t curve, the first portion, this part is a parabola. So, assuming this to be a parabola, we will try to find out the corrected starting point ds, that is the point corresponding to 0% consolidation. We will also then find out the point corresponding to 100% consolidation, and 50% consolidation will be in the middle of this range, and from that we will be able to get small t50 corresponding to capital U50. Once we know small t50, again we use the same formula involving Cv and get the value of Cv. So, the method here is, since this is a parabola, if I take 2 points A and B with ordinates equal, rather the abscissa equal to T1 and 4 T1 respectively, then since this is a parabola, from the starting point to this point, whatever variation in the dial gauge reading is there, that is whatever variation is there in the y coordinate, must also be equal to the variation in the y coordinate between this point and this point. Let us see, that is this ds minus d1 must be equal to d1 minus d2, and both equal to say y. Let us see the reason. The reason is, we have taken the first part to be a parabola, that is time must be proportional to or equal to alpha d square. At all times on the parabola, time must be proportional to d square, because the parabola has an equation of the type y is equal to ax square. This means that at the starting point Ts must be equal to alpha ds square, at point A it should be T1 equal to alpha d1 square, and at T2 it should be alpha d2 square, and since T2 by T1 is 4, we find that on the logarithmic scale d1 minus ds and d2 minus d1 are both equal, absolutely similar, and that is the basis for computing the this distance and arriving at the correct starting point ds. So, we select any two points A and B, this having time T1, this having time 4 T1, and using the difference between this as a starting point, we choose a point ds which will have the same difference in ordinate as shown here. So, that means ds is located. Now, what remains is to locate d100, and d100 is taken as the intersection point of the tangent here and the tangent at the last portion of the curve. These two intersect at a point here, corresponding to which the time is t100, the degree of consolidation u is 100%, and the dial gauge reading is d100. Between these two, somewhere in the middle lies d50 and t50, on basis of which we calculate the value of Cv. So, by making d1 minus ds equal to d2 minus d1, we are in a position to calculate the starting point of the curve. Once we know T50, since it is equal to 0.197, we can substitute that and get the value of Cv. Once again, capital H corresponds to half the thickness of the sample, and since the sample thickness varies during the experiment, we take half the average thickness of the sample for computation of Cv. Now, I had mentioned in one of my earlier lectures, which I am now briefly reproducing, that there are 4 different compressibility parameters: Cc, Av, Mv, Cv. Okay. These are the units, and it is possible to determine all these from this well known consolidometer test. Okay. As a starting point for determining these, we need to know the void ratios. See, we have the dial gauge readings, which we are able to gauge from the experiment, the so called odometer experiment, and we have the time or root of time or logarithm of time as the objective may be. This is a curve somewhat like this, and actually ultimately we are interested in knowing the change in void ratio, because we are finally interested in, for determining Cc, the expression d by d log p, and for determining Av, Mv, we need d by dp. This means that void ratio versus pressure curve is a must. It is unavoidable, it needs to be drawn. This means that it is not always sufficient to just plot the dial gauge reading versus time. That is okay for computation of the coefficient of consolidation Cv, but in order to compute the void ratio changes, we need to make a little bit of a computation based on the dial gauge reading variations, and void ratio computation can be made by again 2 methods. One is known as the height of solids method, the other is known as the change in void ratio method. Let us take a look. In a consolidation test, typically we know the diameter of the specimen, therefore, we know the area of cross section, which is pi by 4 d square, and we know the initial height 25 mm. It is all standardized, it is all fixed, the equipment is an internationally stipulated standardized equipment, and therefore, these dimensions are known. In the 2 different methods, we try to relate the dial gauge readings through the compression of the soil sample to the void ratio. So, in the height of solids method, effectively, essentially we are looking for the height of the soil specimen and how it varies. So, if we know the dry weight of the specimen, we can calculate the unchanging height of the solids Hs by this formula. This is a very well known fundamental formula where Ws by Vs, which is nothing but the density of the solids, when divided by gamma W, gives us the so called specific gravity G. So, we can find out that the volume of solids Vs in any given case will be this G gamma W divided by Ws, okay, or the other way around, Ws by G gamma W. So, the height of solids can be found out as Ws by G gamma W, and actually it's volume, it's a volume, and therefore height can be obtained by dividing this volume by the area of cross section of the specimen. Now, this means that the height of the voids alone at the starting point will be the initial height of the sample H0 minus the height of solids. So, at the starting point, if this is the height of solids and this is the height of initial height of voids, this can be obtained from the initial height of the sample H or H0 minus the height of solids, because the height of solids remains same throughout the experiment, which means that at any instant of time during the experiment, the height of the voids, which will go on changing, will be equal to the previous height minus the change in height that takes place or change in dial gauge reading that takes place. Once we know this, we can calculate the void ratio as height of voids by height of solids. So, the attempt in this method is to determine the change in height of the specimen and relate it to the change in volume of the voids. So, E is taken rather as height of voids by height of solids than volume of voids by volume of solids. So, at any stage HV I, that is volume of height of the voids at time I, instant I, will be equal to the volume of the height of the specimen in the previous stage minus the change in height, and change in height is nothing but the change in dial gauge reading. Okay. A similar approach is there in change in void ratio method. Here we take advantage of the fact that the soil sample is saturated and remains saturated throughout the experiment. Actually, sometimes it may not, but for all practical purposes we assume that the soil sample remains saturated throughout the experiment. Since it is saturated throughout the experiment, we know that the void ratio for a saturated specimen must be equal to the moisture content into the specific gravity again. So, we know the height of solids can be found out from the final height divided by the volume of the solids, that is 1 upon 1 plus EF. If we have several stages of loading, then the initial height minus the total change in height divided by 1 plus EF will always be equal to the height of solids, which remains constant. Because of this, we can say that change in volume or change in void ratio must be equal to the change in height divided by volume of, or rather the height of solids, or in other words E0 minus EF must be equal to total height change divided by height of solids, or it can also be said that E at any instant I minus E at any previous instant should be equal to delta H divided by Hs, Ei minus 1 minus delta H divided by Hs. So, this is the way we can successively compute the void ratio at any stage from the previous void ratio, knowing the change in height and the height of solids which we determined previously. We can therefore now plot either E versus sigma dash curve or E versus log sigma dash curve. If we have the E versus log sigma dash curve, we determine Cc from that. If we use E versus sigma dash curve, then we will be determining other parameters. Now, incidentally, for Cc, for determining the coefficient of compression, that is the compression index, we have another expression, an approximate expression given by Skempton based on a large number of studies by him on normally consolidated inorganic clays of low to medium sensitivity. That equation is one which links Cc with liquid limit. Now, liquid limit is such a basic parameter for a clay that any relationship such as this, where the compression index is related to the liquid limit, is a very useful method for computing the compression index, because liquid limit is anyway determined and it is a very basic fundamental parameter for a clay, and this equation is 0.009 into LL minus 10. Now, let us see an example. To begin with, let us see how to determine the various soil parameters from a typical test. I shall not be going into the details of the data from a test. Let us assume that we have the data. Given the data of dial gauge readings versus the time, we will be in a position to have the basic data required for computing the volume of the void ratio as one of the methods, as per one of the methods which I described just now. And once we know the void ratios, we will be in a position to compute these various parameters. So, suppose E1 and E2 are the void ratios corresponding to two stress values, sigma 1 dash equal to 200 and sigma 2 dash equal to 350. Then this is the change in stress, this is the change in void ratio. If we use logarithm of change in stress, we will be able to calculate Cc. If we use directly the change in stress, we will be able to calculate the other parameters Av, Mv, Cv. Incidentally, the parameter Cc can also be calculated from LL, the liquid limit, and the parameter Mv requires the value of Av, and the parameter Cv requires the value of coefficient of permeability. So, answers are Cc will be equal to the change in void ratio divided by logarithm of the ratio of stress, that is 0.206. We get by Skempton's equation a value very close to this, 0.198. Now, for this load increment, sigma 1 dash minus sigma 2 will be, rather sigma 2 dash minus sigma 1 dash will be 350 minus 200, and Av, the coefficient of volume compressibility, will be nothing but dE by dP, and that will be 0.303, and the units of Av are meter square by kilonewton. Mv is nothing but Av upon 1 plus E. Since we know the starting void ratio, that is the initial volume of the solids, 0.303 by 1.700 or 1.765 into 10 raised to minus 4, again meter square by km, is the value of Mv. Cv on the other hand requires the value of coefficient of permeability, and this is the expression for it, and if you substitute the known values of K and Av and E, you get Cv equal to 17 meter square per year. Let us take another example. A 6 meter thick clay layer is subjected to a load of 60 kilonewtons per meter square. 1 year after loading, the average consolidation U is found to be 50%. So, the time period small t is given, the stress change is given, the degree of consolidation is also given, average degree of consolidation. What is asked is the coefficient of consolidation, assuming one dimensional consolidation, and if k equal to 0.3, what is the settlement at the end of 1 year. The settlement that will really take place here will depend upon the final void ratio. So, we are at this point of time interested in the settlement corresponding to a particular time rather than the total settlement, and that is why we need the coefficient of consolidation here. The solution will be Cv is T50 h square by T, because we know the time corresponding to 50% consolidation. So, we need capital T50, which we know is 0.197. From this we get CV. Obviously, once we know CV, since we know K, we can calculate MB. And it is known that settlement corresponding to 100% consolidation, that is the total settlement, in terms of MV can be expressed like this. Although I have given you the expression for total settlement in terms of CC and in terms of E1 minus E2 by log of P2 minus P1, it is possible to express that in terms of MB as well, and MB into delta P into H will give you the total settlement. So, we know the total settlement in this case from these values of MB, delta P and H, because delta P is known as 60 kilonewtons per meter square, and this gives us 0.609 meters as the total settlement. So, the settlement corresponding to 50% consolidation which takes place in 1 year's time will be 0.304, because 100% consolidation corresponds to 0.609 meters. Therefore, 50% consolidation would correspond to half the settlement, that is 0.304 meters. However, the time taken for 50% consolidation, which is 1 year, need not necessarily be, and in fact will not be, half of the time taken for the total 100% consolidation, for obvious reasons. Now, we come to an important phenomenon known as the pre-compression phenomenon. See, there are many locations in the world where there have been glaciers. These glaciers have come down, melted and come down over great distances and covered vast areas, and at some point of time, for certain unknown reasons, they have retreated. But in this process of coming forward and going back, they had been responsible for applying enormous amount of loads on soils, particularly what is of relevance to us are clayey soils. There, the clay soils which have experienced this have undergone consolidation under the load of these glaciers, and after the glaciers have retreated, they still remain consolidated, but they are more consolidated than one would expect under the present overburden pressure. So, such soils are known as over consolidated soils. We need to know in such soils what is the degree of over consolidation, or what is the compression pressure to which it has been subjected to in the past. This is important. Suppose you see this graph which I am showing here. If I apply load on a sample and observe this void ratio change, I know that I will have the so called virgin compression curve up to some stress, and now if I unload and reload, the soil traces a totally different path until it reaches the same pressure at which we started the unloading, and beyond that once again it passes through a almost straight line curve, which again is a virgin compression curve, because this soil is undergoing this degree of compression under this stress for the first time, whereas any soil which starts at this point would have already undergone compression to this level and would have, that means, experienced a peak compression pressure corresponding to point C. This means that from this graph of loading and unloading, it is possible to find out what is the pressure to which a soil has been consolidated in the past. There is a graphical procedure, and this is a very simple graphical procedure. You take the void ratio versus pressure curve plotted to log scale, draw a tangent at a point corresponding to the maximum curvature, then also draw the horizontal at that point, then the bisector of this angle, and where this bisector meets the straight line extension of this curve BC, that is this point P, that gives you the maximum pressure to which the given soil has been subjected to in the past. Now, this soil being over consolidated, we can find out what is this value of P max compared to the pressure P that it is now experiencing. Suppose this pressure P now which is experiencing is less than P max, then the soil is under consolidated. If this is equal to P max, then the soil is normally consolidated, and if it is more than P max, it is over consolidated. Or to put it in other words, if the maximum pressure to which a soil has been subjected earlier is more than the present overburden pressure, then the soil is over consolidated. There are many reasons for over consolidation. I have explained particularly the glacial retreat as the main reason. There are other reasons as well. So, in this lecture we have understood the importance of the consolidation equation. We have seen how the odometer test can be used for determination of the coefficient of consolidation and also the void ratio changes, and then we have seen a few examples. We have closed the lecture with a discussion on pre-compression, and we shall now pass on to some other topics in the next lecture. The topics will be the so called secondary consolidation and the radial consolidation, which also again we will follow up with a few examples.